Okay, a very good morning to all of you. It's a pleasure to welcome Professor Somak Raychaudhury this morning to speak to us on galaxies and their supermassive black holes. Somak, as you all know, is a director of IUCAA, and he's worked on a very broad spectrum of topics in extragalactic astronomy, ranging from galaxies to groups and clusters of galaxies, large-scale structure, active galactic nuclei, using data at a wide range of wavelengths, be it optical, radio, or X-rays. And it's a pleasure to have him with us today to speak on galaxies and their supermassive black holes, an exciting area of research with a lot of new results coming in, particularly from the Event Horizon Telescope as well as other telescopes. Over to you, Somak.
Thank you. Thanks, Vitzak. That's wonderful and wonderful to be here. I mean, the Radio Astronomy School is one of the most important and oldest activities ongoing in IUCAA, and I think I've been part of it for a very long time, and it's wonderful to see all of you participate in this. As opposed to many other workshops, this is more hands-on, but I'm glad that there are lectures to back up the hands-on activities that we've been doing. I hope you've been enjoying all that. Because there are only a few lectures associated with this workshop, not all areas of astrophysics can be covered. And I know in Galaxies, you already have had quite a lot of lectures. You've had lectures on central galaxies and clusters, jet slopes, activity, central activity. You'll have more lectures on AGN. Yesterday, you heard about our own galaxy, the Milky Way. I just wanted to concentrate on the effect of the supermassive black hole in the middle, and very briefly talk about the evidence of the supermassive black hole in the middle of galaxies. Just to start off, you know that there are the universe is made up of galaxies. The basic unit, the building block of the universe, is a galaxy, and there are two different kinds of galaxies. Generally, I mean, there are the spheroidal galaxies, which are bulge-dominated. They are older populations of stars, and they look nice and round without much rotation, much dust and gas, and they are about 20% of all galaxies in the universe, roughly. And then there are disk galaxies, which are galaxies one, which have spiral structure in them, and these are, of course, we're talking of the giant galaxies, the galaxies that are roughly our size or more. And these galaxies interact with each other, they merge with each other, they do all kinds of things, and they exchange gas and stars and dust. So these are the universe is quite dynamic. And we also saw what our galaxy looks like, and we are not in the center of our galaxy. We are offset from the center. Galaxies have all these components in them. Of course, the main component put on top is stars. These are the baryons, the baryonic component, the component that's made up of protons and neutrons and things like we are made of. And that's the stars, the gas, and the dust. The gas can be hot gas, can be cold gas. And so you have to observe these things in different parts of the electromagnetic spectrum. Because hot gas, you see in X-rays, the cold gas, you see from the 21 centimeter transition in the radio. There's the molecular gas, which you can see more in the millimeter waves, things like that. So the different kinds of the gas are very, very important, because the roughly equal amount of matter in the gas and the stars, the baryonic gas, actually the hot gas is slightly more in proportion in galaxies than even the stars. And then there are magnetic fields and radiation of various kinds. There's the main mass component, of course, is dark matter, which can't be seen but can be felt. The gravitation, it's dark matter that's holding the galaxy together to some extent. But one of the focus of today's topic is the central engine of the galaxy. And I say sometimes because we find these central engines, this black hole and associated accretion disk around the black hole, the supermassive black hole in galaxies above a certain mass. Not all galaxies have them. The dwarf galaxies don't. In general, there are exceptions, but galaxies that are roughly similar to our mass or more seem to have invariably a black hole, a supermassive black hole in the middle. The other things are distributed, and you'll see the significance of this later on in various parts of the galaxy. The population of compact stars, for example, you see mostly in the disk. The halo population, are older things like globular clusters. There are various kinds of populations of various kinds of stars in the galaxy. I'll concentrate on the on the disk and in particular on the black hole in the middle. But you will see how when we try to understand how these supermassive black holes form and how the galaxies form, these will be very important. What are black holes? We know that they are a consequence of general relativity, which says that massive objects curve space-time, and the more massive an object is, and the combination of the size and mass tells you how far space-time is curved, and so if this kind of represents space-time, then very dense, massive objects like black holes curve space-time a lot, so much so that even light can't come out of these deep potential worlds. So this is the idea of this form of Einstein's general relativity, which essentially says the geometry of space-time is connected with the curvature. It's connected with the mass, the gravity of the kind of definition of gravity. Now, how big is a black hole? It comes from, I mean, this has been asked from Newtonian times. People used to think about black holes. They were not called black holes then, they were called dark stars. Even in Newtonian times, in terms of an escape velocity, and asked the question, what if a star was very small, so small that even light couldn't come out of it? It would be a star we could not see. Actually, the black hole cannot be described in terms of Newtonian mechanics because you are dealing with velocities that are very close to the speed of light. So you needed Einstein to formulate such a description of gravity. But then the question remains the same. How can space-time be curved enough that even light cannot climb out of it? And the nature of space-time around a massive object is given by the Schwarzschild metric. And so the event horizon, which is the radius out to which you can see around a black hole and light cannot escape from it, is called essentially the size of the black hole. And it's also known as the Schwarzschild radius. It's given by a very simple formula. It comes out of the Schwarzschild metric. This is not something that you can get very easily out of Newton's laws unless you make certain very extreme assumptions. But it's very similar to the escape velocity formula that you're familiar with in Newtonian mechanics. So the Schwarzschild radius essentially shows you that it's the size of the black hole is proportional to the mass. Which means that if you take the Earth's mass, the Schwarzschild radius corresponding to the Earth can turn into a black hole if you can squeeze it to below 1 centimeter radius. It's hard to do. The sun can become a black hole and it won't in its natural progression during its lifetime. But it would be if we can squeeze it to below 3 kilometers in radius, and that will be the event horizon around the Schwarzschild radius of the black hole that will be the sun. Now, in the middle of galaxies, you have, and you will see black holes that are much more massive, millions to billions mass of the sun, and their Schwarzschild radius will be disproportional to the mass. So there'll be 1 billion kilometers if there are 1 billion solar mass black hole, right? So that's the formula to keep in mind. Very simple formula. The size of a black hole, the size of, when I say the size of a black hole, I mean the size of the event horizon, the size of the radius out to which you cannot see anything come out of the black hole, any information come out of the black hole, and that is proportional to the mass, right? So simple formula to remember. So this will come back later on when we talk about detecting black holes. Galaxies have many, many different kinds of black holes. We know that, of course, stars evolve into black holes. So stars can, at the end of the life of very massive stars, some stars can turn into black holes. The remnants of stars as the outer parts blow up. But then these remnants of black holes, remnants of the stars that turn into black holes would be smaller in mass than the most massive stars. The most massive star that we've seen in our galaxy is about 100 times the mass of the sun. So these stellar mass black holes are black holes that are of the order of a few times the mass of the sun. The most massive stellar mass black holes that we have seen right now from gravitational wave measurements, LIGO, is about 180 times the mass of the sun. But those are, we actually see them as the gravitational waves are detected as the black holes merge. So we saw, for example, two black holes of about 80 times the mass of the sun merging to form a higher mass black hole. So most black holes, that stellar mass black holes that we see in galaxies, are much less in mass, a few times, 5 to 10 times the mass of the sun. And I'll show you a couple of examples later on. There are, of course, as I said, the supermassive black holes. Each galaxy has one in the middle and right in the middle, and those go from millions to billions times the mass of the sun. And now we are, courtesy of LIGO, finding these black holes in the middle. For a long time, people worried about what happened. Why aren't there black holes of intermediate mass? Because if you think of these supermassive black holes forming by merging smaller black holes, then all the way you should see masses, a range of masses. And that kind of tells us that maybe the supermassive black holes are not formed by stellar mass black holes merging because there is this mass gap in between. But recently, as I said, we've started seeing the two cases in which we've seen masses of black holes that are higher than 100 times the mass of the sun. And we've seen smaller black holes merge to form these things from gravitational waves. So these mid-mass black holes are being found now. Thousands haven't been found, but these are, I think, will come as more and more observations come. So there are these different kinds of black holes. Our own galaxy, you saw, has in the middle a supermassive black hole in the of the order of 10 to the power 6, 4 times 10 to the 6 times the mass of the sun. And I'll repeat a little bit of what Professor Saikia said yesterday about the Milky Way, because this is the nearest supermassive black hole that we can see. A lot of our evidence of supermassive black holes depends on knowledge of the supermassive black hole in the middle of our galaxy, and that's from the dynamics of stars near Sagittarius A star, which is the central source in our galaxy, which you can't see, of course. But if you want to look at the motion of the stars, which you saw yesterday around them, and I repeat this because this will be important for the other discussions as well. I want us to understand, because we are, all of us, here are actually doing hands-on work. So understanding the scales and the resolution is very, very important. Even in our galaxy, if you want to see stars very close to the center of the galaxy and to look at their dynamics, you really have to have exquisite resolution. And this, the evidence of the supermassive black hole in the middle of our galaxy comes from near infrared observations. Because as you know, you saw that in our galaxy, if you're looking towards the center of our galaxy, you look through the dust. You have to look through the dust. And this dust, there's a lot of dust in the disk of our galaxy. And this dust obscures optical light. You can see it's pretty black. This is not a real picture. This is an artist's impression. You can't take a picture of our own galaxy being inside it. But the dust obscures the optical light from the stars near the center of our galaxy. And so you go to near infrared where the dust becomes transparent. And here you're looking at the star clusters, which is at 2 microns, which is the near infrared wavelength. And you're trying to find out from the dynamics of these stars what this galaxy looks like. So I just quickly do a couple of calculations of how to look at angular sizes. The actual size of a star is very, very small. The star, if you look at the angular diameter of a star, if you take the sun and take it at 8 kiloparsecs, which is the center of the Milky Way, the distance between us and the center of the Milky Way, its angular size is going to be about, you know how to calculate this. It's just the diameter divided by the distance and in radians, and they've been converted into arcseconds. It's a micro arcsecond. So, so these are, and of course, when we take pictures from the Earth, the atmosphere blurs the images because of the differential refractive index of the various layers of the atmosphere. It blurs to about an arcsecond or a fraction of an arcsecond. So you really can't resolve the actual size of any star. You only see a blurred version of it. Now, if you want to go very close to the galactic center, the Schwarzschild radius, the Schwarzschild diameter of the central black hole in our galactic center at 8 kiloparsecs is a few micro arcseconds, right? So not micro, it's micro arcseconds are a millionth of an arcsecond, right? So you're talking 10 to the power minus 5 arcseconds here. So you really can't see the actual diameter. Now, of course, the Event Horizon Telescope has an image which hasn't published of really that level of micro arcseconds. And we'll come to the other thing that they have published, the picture of near the event horizon of the black hole in M87. But these are extremely high resolution images that you have to do. The normal resolution of, if you want to resolve out the stars that are orbiting the central black hole, even in our own galaxy, what you have to do is go up to milliarcseconds, the minimum separation of the nearest stars around the Sagittarius A star S2, which you'll see in a minute, is about 100th of an arcsecond. And to do that, what you have to do is to use adaptive optics. And that means that the whole telescope's mirror has to be adjusted such that the focus remains the same, even though, so to cancel out the effect of the atmosphere. This is an amazing development in technology. In IUCA, we do quite a lot of adaptive optics. And the Keck telescope, which was used for this, does adaptive optics. And so, for example, without adaptive optics, the galactic center in 2 microns, where these things are observed, would be a total blur. You won't see the individual stars, but you do with adaptive optics, because you can have the resolution, which is about 100th of an arcsecond, actually not so good, but almost near that. And so these 2 people got the Nobel Prize, as you know, for doing this. And you saw this video yesterday of the stars around the central bit of our black hole. And I want to point out that this is a 10th of an arcsecond, so you can see the resolution of these stars going around the central black hole. And from that, one uses Kepler's laws, and you saw yesterday, measure the mass of the supermassive black hole, and that's 4 times 10 to the 6, right? Times the mass of the sun. So this establishes that there is a supermassive black hole in the middle of our galaxy. Now, does that establish that it's a black hole? This is the crux of the matter. And so you see this is one of the stars. This is S2, and there's an elliptical orbit, and you fit a relativistic form of Kepler's laws and find this, right? But you have to, in addition to finding the mass using Kepler's laws of the black hole, which is 10 to the 6 times the mass of the sun, you have to establish that it's a compact object and not a cluster of stars, for example. right? Globular clusters have masses 10 to the power 6 times the mass of the sun, right? But you know that the Schwarzschild radius, just scaling from that relation I showed you, of this black hole in the center of our galaxy would be millions of kilometers, not parsecs, right? And so the size of a globular cluster is a few parsecs. Size of a globular cluster that's 10 to the 6 times the mass of the sun would be somewhere between 5 to 10 parsecs. Whereas here, the minimum distance that these stars go to the central, the black hole, which is at the focus of this ellipse, is only slightly larger than the size of the solar system. And so this means that if this were a globular cluster, this would have been much bigger and this star would have collided with it, right? So it just shows that it's a very compact object. It gives you an upper limit to the size within which this 10 to the power 6 times the mass of the sun has to exist. The fact that the star has gone and come around and not collided with it here, and that is what establishes is essential as a black hole. That's very important. To establish the existence of supermassive black holes, you have to measure its mass and measure its an upper limit to its size, and you have to establish that it's consistent with a single star and not a group of stars. And that's the most important thing. And this is why I repeated what you saw yesterday, just to show that this, even from our own galaxy, the existence of the supermassive black hole has to have these. Now, this is the best studied example of a supermassive black hole in the middle of our galaxy, because you can actually see the stars going around it and measure the mass as you would measure the mass of the sun from the planets going around it. Now, this is very difficult to do in other galaxies. Currently, with the resolution that you have with our telescopes that we have with us, we cannot resolve these stars going around and follow them year after year after year. In other galaxies, we can do other techniques, but in future, much bigger telescopes, which will have much better resolution, will be able to do this. Right?
Can I ask a question?
Yes, please.
So this S2 was tracked using adaptive optics approach?
Yes.
I see.
So here you are, you can see the Keck telescope, and the Keck telescope and the VLT both have adaptive optics. So the Keck telescope has 36 mirrors, which are completely, they are hexagonal and they're put together to make up the 10-meter surface. And what happens is that the mirror itself changes its shape in order to keep the focus. And this is, I mean, the Nobel Prize that these people got was not because of finding the black hole, but developing the technology to do this. And the most important bits of technology that come into here, a place here, are A, the technology for observing in the near infrared and imaging at these high resolution. That is itself happened in my lifetime. When I was a PhD student, we were using the first near infrared sensors that became available now. So it's only 25 to 30 years old, this technology. And secondly, one had to, I mean, to actually have the kind of resolution of a 50th of an arc second from a terrestrial telescope can only happen in adaptive optics. And this is also technology that they had to develop in these telescopes, both the VLT as well as the Keck. These are the two telescopes that these two people used. And then so that's the bit that gets you the Nobel Prize, not the fitting of the Kepler law to an ellipse.
Thank you.
So, right. So this is again is one way of doing it, but it's a very hard way of doing it. This took them, as you can see, from 95 in the case of Angio-Guess, in the case of Genzel from 92 to now, to be able to actually monitor stars that go around it. And it's amazing that these stars have periods of 15 years. But to do that in other galaxies is very difficult. So let's look at what else you can do to find these galaxies, find these black holes elsewhere. Stellar mass black holes. Okay, yes, another question, Kostub?
So at such small distances to the black hole, do we not expect deviations from Kepler's law?
Yeah, this is what I'm. So here I've just written. You're right. I've written just the Kepler's law here, but the actual ellipse that's fit here is a relativistic version of it. Yeah, which I didn't write down because you can't write down like that.
Okay.
But yeah. So if you look at the original paper, you will see what kind of formula they used. But basically, that the numbers come out similar. Yes.
Yeah, thank you.
Yeah. Yeah, of course, very near. I mean, if you're fitting an orbit to a star orbiting the black hole, you need relativistic corrections. Okay, so just to look at how you would, the more common way of finding black holes in the past has been to look at X-rays because of the following. What happens is that you, and you get them in binary stars. They're not supermassive black holes, but just to illustrate how most black holes are found, I thought I'd show you this sequence of slides of how a binary evolves. Most stars in our galaxy are in binary systems. So for example, you'll have two stars, one smaller than the other. And the more massive star will evolve much faster. It might go supernova and create a black hole. If it's massive enough, say more massive than 4 or 5 times the mass of the sun. And then it'll be left with a normal companion. The normal companion in its time will also evolve to become a red giant, and its outer layers will become have less gravity than before, pulling it to the star because the star is now much bigger. And so it might be that the companion black hole will pull its mass out of the star, but this mass that's falling onto the black hole will have some angular momentum, and that can't be got rid of, and so it will form a disk around the black hole, and these are called accretion disks. Now you heard of similar things in the context of supermassive black holes as well, in the centers of galaxies. You will hear more when you hear the talk on AGN, but accretion disks are common around black holes, and these, because the gas cannot fall straight into the black hole because it has to preserve its angular momentum, and for other reasons that I'll come to later, the gas around the black hole exists. Now this black hole that is that gray circle there might be the event horizon of the black hole that you can't see, but the surrounding gas, which is in the accretion disks, it sits around the black hole for a long time, orbiting it. And so it can get very, very hot. And these things become very hot and they emit in the X-rays. This is an artist's impression of such a system in which you can see that the accretion disk around the black hole gets very hot. Now, these things can get as hot as 10 to the power 6, 10 to the power 7 degrees, and at 10 to the 7 degrees. The predominant radiation it emits are X-rays. Now, as you can see, the X-rays have very short wavelengths. They are of the order of nanometers, which are in this range, and so these are very difficult to focus. These because they will go right through material, because the interatomic spacing of most solids are nanometers. So X-ray telescopes are made in a very different way than optical telescopes. In the case of radio, it's the other end. As you know, in radio, the wavelength is much, much bigger. And so reflecting these waves of very rough surfaces is possible. And you've been learning more about that. And the second thing is, as you know, in the atmosphere is not transparent to X-rays. In the optical and in the radio, it lets in electromagnetic radiation. So you need space telescopes to observe in the X-rays. And so this is a good example of a space telescope that has been observing these black holes, both supermassive and stellar mass black holes, Chandra X-ray Observatory. We also now have our own Indian observatory in space, AstroSat, which is also doing a very good job in doing similar things. Chandra was actually launched to find these black holes. And it has these very long orbits taking them away from the Earth's radiation belts. But the most important thing is that it has these mirrors, and our AstroSat also has a version of these mirrors, not as good in resolution, which focus X-rays through grazing incidents, not normal incidents. Normal incidents, X-rays go right through. Grazing incidents, the effective interatomic spacing or intermolecular spacing of the mirrors becomes much smaller. And so you have to actually have the X-rays be incident on the surface at angles much smaller than a couple of degrees. And so this is why these telescopes are built very long. And you can see that the X-rays would enter through here, and this is about 5 meters long, the mirrors, and at the end would be the detectors that would detect these X-rays. And the Chandra in particular is the only observatory up there that has exquisite resolution. It is resolution, sub-arc second resolution, and it can actually form images of these individual accretion disks around stars. Now you will have accretion disks around the black holes and neutron stars in binary star systems. These are the stellar mass black holes. But you will also have gas around the center of the central supermassive black hole, and that will form an accretion disk that will form all kinds of effects, and that will also emit X-rays. And you can see in the case of this, and so here's an example of from my own work, where I can show you black holes of both kinds in the same plot and the same observation. This is, of course, an optical observation of Centaurus A, which is one of the nearest early type galaxies, the nearest early type galaxy to the Milky Way, actually, about 5 megaparsecs away. And this is an S0 galaxy, which has had a recent merger. We know that there's a supermassive black hole in the middle, and which is very, very massive. It's 10 to the power 8, 10 to the power 9 times the mass of the sun. And it's right in the middle of this, this dust lane. But here in this particular picture, you can see this is an optical picture. So what you're seeing here are normal stars, which are a few thousand degrees hot. You stare at this galaxy, and we had quite a lot of time, about 1.5 million seconds of time over the last 20 years of accumulating X-ray data on Centaurus A, and this is what you see in Centaurus A in the X-rays. And everything that you see here is 10 million degrees hot at least, right? 10 to the power 3 degrees hot, 10 to the power 7 degrees hot. Same scale, same galaxy. And here what you see are these X-ray binaries, which are either neutron stars or black holes coupled with normal stars, and you're seeing the glowing accretion disk. But what you're also seeing is right in the middle of this galaxy, right here, the evidence of the supermassive black hole, because you can see the gas around it. And the fact that the supermassive black hole is so active, it is blowing a jet. You've heard of jets before. In the case of radio jets, this is an X-ray jet that's been ejected by the central black hole, because the gas that's falling into the central black hole cannot fall in at the rate that it wants to, because there's a lot of gas falling into this central black hole, so it's ejected at relativistic speeds. This jet is moving close to the speed of light, and it's 10 to the power 7 degrees hot. And from the energetics of the jet, which can be measured, as well as the temperature of all this, it can be modeled, you can actually find the mass of that black hole, right? So you can detect the black hole, you can find the mass of the black hole, you can establish it's a black hole, because the black hole models will predict the energetics of the jet that's ejected from it. So in this particular plot, you can see in X-rays both the stellar mass black holes in binary systems. You can also see evidence of the central black hole in this particular galaxy. And this is from X-rays, very, very independent of the dynamical picture that you saw in our galaxy. In our galaxy, from getting X2 and things like that, you really had to go to microsecond or millisecond, in that case, millisecond resolution. In this case, you don't need that. This is just sub-arc second resolution, but you see the gas around the central black hole, and that doesn't need that kind of resolution. You had to go to space, not because of the resolution, but the fact that you need to detect these X-rays, which you can only be got to space from space.
So I have a question.
Yes.
Sir, of late I read that scientists have detected the light from the back of a black hole or something like that. Like, can you please briefly explain, like, what is that thing?
I'll come to it in a minute. Let me just talk about the black hole. The observation will come to it.
Okay, sir, fine.
So people have been targeting these supermassive black holes for a long time. Nearest elliptical central galaxy is M87, which is the center of the Virgo cluster, 15 megaparsecs away. People tried to do this. People tried to get with the Hubble Space Telescope in the middle of the galaxy and to find what is suspected to be 3 billion times the mass of the Sun, galaxy in the middle. And one could find just the gas disk in the middle, which is glowing in various kinds of radiation. HST would get the ultraviolet and optical radiation from the different parts of the of this disk. As you can see, you really from HST you get about 0.1 arc-second resolution, but we calculated that in the center of the galaxy, even in our galaxy, the actual size, the event horizon of the black hole is of the order of a few tens of microseconds. You can't get to that kind of resolution, but the accretion disk around the black hole, even at 15 megaparsecs. See, our black hole, the black hole in our galaxy is 8 kiloparsecs away. You're looking at the central bits of nearby galaxies, which are megaparsecs away, 1,000 times further away. So they have become 1,000 times smaller, but the accretion disks are much, much larger than the event horizon of the black hole. So you only need arc-second resolution, and you can actually figure out and then you can try and find the rotations and the motions within the accretion disk of gas, not the individual stars that are near the black hole. And so that needs only arc-second resolution. And from that, people in the early days of the Hubble Space Telescope measured the rotations in the central disk of the black hole, a central disk around the black hole, and tried to find the mass. This is what you're talking about. This is here you are looking at a direct image of the light coming just outside the event horizon of a black hole. This is now, as you know, became the front page picture of newspapers a couple of years ago from the Event Horizon Telescope. We call it the direct imaging of the black hole because here the resolution of this image is 10 micro arc seconds, 10 to the power minus 5 arc seconds. You're actually going to the resolution of the 10 to the power 5 solar mass black hole, 10 to the 9 solar mass black hole, and you can find out what its Schwarzschild radius will be, what it looks like, what it would be in arc seconds at 15 megaparsecs, which is at the distance of the Virgo cluster, and you will know that is measured in a few micro arc seconds. And so this requires that kind of resolution. And what you're seeing here is the light coming out from just outside the black hole. Now, what happens in the case of the black hole like this is that even though the event horizon is 2 gm over c squared, you the near the smallest radius a stable stellar orbit can have is a few times outside the event horizon. That's called ISCO, the least stable orbit. And then you also can see photons escaping from just outside the event horizon radius. It all depends on the detailed physics of the black hole, the radiant black hole that I'm not going into, but it's about 3/2 of the event horizon radius is the last photon that can come to you. So it's not just from the event horizon, but just outside the event horizon. And for a stellar mass black hole for 3 solar masses, this is that kind of radius, and you can scale that to 10 to the power 9, and you would know what the resolution of the photon sphere will be. That the photon sphere being the innermost photons that you can see coming out of the black hole. So those are the pictures that we saw. And here too is what somebody asked just now, is an evidence of the asymmetry of the sphere that was seen. Because the resolution was so good, this is resolution of a few micro arc seconds here. The image that was published of the M87 black hole, which is roughly similar to what you expect from our own black hole, our black hole in the central part of the Milky Way, which has not been published yet, but the resolution would be the same, because remember, the black hole in the middle of the Milky Way is 10 to the power 6 times the mass of the sun. This is 10 to the 9 times the mass of the sun, and it is 1,000 times further away. So the angular sizes are roughly the same. The asymmetry tells you that you see the photons from the back and the front and the sides of the black hole in a manner which shows you how the space-time is warped around the black hole, and so you see lensing effect. You see, and you can actually see the black hole, the light from the back of the black hole come around the black hole to the front. And the event horizon, I don't have a slide showing you the new pictures that have been published, which were alluded to, of imaging much more than the front part of the black hole using this technique. And you've seen this, of course, in movies. Interstellar, for example, showed actual simulations done by astronomers of what the material around the black hole would look like, and how much you would see it if you're looking at it from a distance. As you know, in the movie, real astronomers including Kip Thorne, were involved. And this is one of the things that people want to do. But just the asymmetry of this image shows you that you don't see the photons coming from all parts of the photon sphere, or even the accretion disk in X-rays, in a symmetric fashion. If you have the right resolution, you can see the radiation being lensed. As you know, the Event Horizon Telescope used interferometry in the best way possible. You've been learning about techniques of interferometry, radio interferometry, and the Event Horizon Telescope observes in millimeter waves, which is same technology. And used to get this 10 to the power 5 minus 5 arc second resolution. To get this kind of images, one needs interferometry that is done across the Earth. So you have a telescope the size of the Earth. And in order to get the resolution you need to find an image of the heart of the Milky Way, you need the same thing. And you see, you have these telescopes right from the Antarctica to Europe to Hawaii, and to have this kind of resolution, you need these baselines. These baselines give you the resolution. Right? So that's the direct imaging, and because this is only the beginning of the story, this will also undoubtedly lead to a Nobel Prize. And this is only the beginning of this technology, and you will see more and more of this high resolution imaging of the centers of galaxies. There are other ways of finding these black holes, and not just so. The next two things I'm going to deal with in the rest of my talk today will be some techniques of finding these black holes, but also what do they mean? I mean, what do we gain out of finding these supermassive black holes and trying to understand them? And what I would argue is that they tell us they have very crucial information about how galaxies form, how matter forms into galaxies in the universe in its lifetime. So I'll give you a few examples. M106 is a good example, which has been studied for a long time. It has a major emission in the disk from the gas, the cold gas in the disk, and this can be traced, and from the major emission, very highly accurate velocities can be measured, and if the things are slightly at an angle, not just face on, but the galaxy has an inclination, you can measure the Doppler shifts very accurately. And this leads to something that's 30 times, 30 million solar masses. And so this is a galaxy that looks very much like our galaxy. Now, to establish the existence of supermassive black holes, you need to do two things. One is to find a way of measuring the mass, as I said, and also to measure the size. Various ways of doing it. I told you about the stellar kinematics in the core of the galaxy, in our galaxy. You can also measure the spectrum of optical light emitted very near the black hole in this optical spectra of AGN, active galactic nuclei, and quasars. And the width of the spectral line tells you the Doppler broadening of the material that is actually emitting this radiation. And so the width of and the Doppler broadening gives you some idea of the velocities in that particular system that is producing the radiation. This is the broad line region in the heart of the galaxy, and that can tell you the mass of the black hole. From X-ray spectra, there are some cases. So here is an example of the broad line, the broadening of optical spectral lines. You can see that here's a spectrum of a Seyfert galaxy, Seyfert 1 galaxy, Seyfert 2 galaxies. Then you have these very broad lines, and from the line, the width of the line you can measure the actual the Doppler effect, which means, and it leads to velocities that can be a few thousand kilometers per second. And you go, if you can manage to have a very high resolution, you can go very close to the black hole. This tells you, it's very similar to the measuring the orbital motion of stars. You're looking at the orbital motion of the gas, that gives you some. Another very early but important evidence of these supermassive black holes has been the existence of very highly ionized lines from atoms that are very high up in the periodic table. Like iron, for example, the iron K line is essentially a hydrogen line, hydrogen-like ion atom, which are essentially and its rest energy is at 6.7 keV, and you can measure it in the spectrum of the gas that's being emitted in X-ray emitting gas in the center of galaxies, and the existence of this line tells you the energetics of the general region, and you can only see this from the shape of the line and the asymmetry of the line. You can measure the Doppler shifts that are there in the gas that is emitting this particular ion line, and that also tells you about the mass of the central black hole. Finally, we talk about what these black holes are doing in the center of the galaxy. So we know that galaxies have disks and bulges. I told you initially that if you look at our galaxy is a small bulge, and then there's a disk. If you look at the various kinds of galaxies, you have the early type galaxies, elliptical galaxies, which are essentially bulges. There's no disk in it. And then you have the very late type galaxies, which are essentially disks, but there's no bulge in it, very small bulge. Our galaxy is somewhere in the middle here, and we have a small bulge, and there's a disk, right? The disk is the young part. There's a lot of young stars, a lot of star formation going on. The bulges in spirals are very similar to the elliptical galaxies. They are mostly older stars. They are not rotating much, and they've been slowly accumulated over the age of the galaxy. Right? So this is an interesting thing to know, that you can divide a galaxy into its bulge and its disk, and their origin is pretty different, because and you can see their properties are very different. The disks are blue, the bulges are red, older stars, and they are more connected with the halo population of globular clusters that I showed you before. The galaxy has a population of older stars, older star clusters, globular clusters that are the oldest parts of our galaxy. They are connected with the bulge, and the disk has a lot of the newer material in it, the gas and the dust and the younger stars. So where does the supermassive black hole fit in? And it turns out, and this was pointed out very early on in the 1980s, 1990s, is that when people started measuring the masses of the supermassive black holes, it turned out that they are correlated, and these are results from nearby galaxies, correlated with the bulge mass of these galaxies. So that kind of explains why our galaxy has a 4 million times the mass of the sun supermassive black hole. And an elliptical galaxy like M87 has 1 billion times the mass, the sun's mass black hole. And that is because the mass of the black hole, which is on the y-axis here, correlates with the mass of the bulge of a galaxy. And spirals have smaller bulges, larger disks. Most of the mass is in the disk and much smaller bulges. And so the supermassive black holes in spirals are small. In the elliptical galaxies, all the galaxies are bulge. And so the entire galaxy is mass. So here are two proxies of the mass of a galaxy. On the left, you have a plot in which the x-axis is the luminosity, the K-band magnitude, K-band luminosity, K-band being in the infrared, near infrared, which gives a better idea of the total amount of light coming out of a galaxy, because in the blue, a lot of the light is dominated by hot stars, young stars, and also they are absorbed. So to get a good idea of the mass of the stellar mass of a galaxy or a part of a galaxy, it's good to observe in the K-band, in the near infrared. So this is the K-band mass of the light of the bulge. It's like mass. And on the right, the x-axis gives you the velocity dispersion of the bulge of the galaxy. And the velocity dispersion is essentially the random motions of the stars in the bulge. And that comes from the width of the emission or absorption lines in the optical spectrum of a galaxy. Right? The width tells you the stars are giving you the spectrum, as opposed to the gas spectrum I talked about before. It is the spectrum of the light of the stars, and then the random motions give you the width, right? And you can see the very nice correlation. These are log-log plots, very nice correlation between the mass of the black hole and the mass. There are two proxies, the velocity dispersion and light of the bulge. Now, this mass of the black hole does, as I said, but does not correlate with the mass of the disk. So here's the same galaxies, but now you have the they are the mass of the disk, and then there are certain galaxies which have no bulges, etc., but it doesn't matter. These are disk masses or disk luminosities, and they don't correlate. So it's very clear that the mass of the supermassive black hole correlates with the mass of the bulge. It also is correlated with the kind of star formation history of the galaxy, of the universe. So this is in this plot. Even though it does not correlate with the mass of the disk of the galaxy, if you look at, and I'm not explaining this in great detail because that will take another lecture, one can figure out the growth history of black holes. And this is based on some kind of a model, based on the central black hole being fed by accretion of gas and stars, and it's growing, and that's the model on it. On top of it is superposed actual measurements of star formation, the star formation history of galaxies as a function of redshift. And as you go to high redshift, you're going back in time. And you know that these things peak at about a redshift of 1 to 2. And we find that when we look at supermassive black holes at different redshifts, and we really haven't found supermassive black holes and measured their masses in very, very high redshift yet, but you can extrapolate from what we find as in the evolution within our nearby population, and we find that kind of peaks around that time. So that's telling us something. Another thing that the supermassive black hole mass correlates with is the number of globular clusters in a galaxy. It's very interesting. So here you see it correlates with the bulge. It correlates with the older population, which is the population. This is why I talked about the halo population around the galaxy, the globular clusters. And so that is telling us something. We also know that all galaxies don't have a supermassive black hole, right? So below a certain, so here, for example, the different symbols colors are as follows. So here is the mass of the central massive object, now I'm calling it, because not all of them are black holes. And here's the magnitude of the bulge, here's the velocity of dispersion, etc. And you can see that below a certain magnitude, and that is our galaxy's bulge is of the order of just below -20 here. And for smaller galaxies, the central massive object is not, there's no evidence that it's a black hole. In fact, in many cases, it looks like it's a massive star cluster, right? So we know that the dwarf galaxies, the smaller galaxies, this goes down to pretty small galaxies, small ellipticals, for example, the most ellipticals, small ellipticals between -15 to -18, 19 in absolute magnitude, and they don't seem to have supermassive black holes in the middle. So essentially, what all this points to is the fact that galaxies and their bulges have co-evolved. They have evolved from the very beginning. The bulge itself has slowly built up over the age of the galaxy, and it looks like the central supermassive black hole was there knows about the mass of the bulge and the evolution of the bulge and the evolution of the halo population. And that's why the Megorian relation and these relations, the correlations that I talked about, are very, very important, because it talks about, indicates that the black hole growth is connected with the older population of the galaxy. And in younger galaxies or in dwarf galaxies, these supermassive black holes are not really correlated or don't even exist in the smaller galaxies. So this is telling us something about how these supermassive black holes form. There are actually alternative theories about the formation of supermassive galaxies. So the one I'm talking about is that the supermassive black holes form very early on. They even can seed these galaxies, and the galaxies have these black holes grow by accretion throughout the age of the galaxy. These black holes would probably form when the universe is very small. They won't form for stars. Stars cannot give rise to supermassive black holes. Even it has been argued that even though you see in LIGO stellar mass black holes coalescing to form larger and larger black holes, that star mergers, stellar mass black hole mergers can't really give rise to these supermassive black holes because you don't see the intermediate one yet. And also the age of the universe is pretty young. And to have so many mergers go from 5 solar mass black holes to 9 solar mass black holes is very difficult. So black holes would form in very early on in the age of the universe, along with when the galaxies are formed, or before the galaxies are formed, and they grow with the older population of the galaxy connected with the intermediate mass, the supermassive black hole, and the newer populations are not. It tells you that the galaxies and black holes evolved together, and somehow the evolution of the various parts of the galaxy connected with the evolution of these black holes. This is where the subject stands now, and it's very, very interesting. So it just tells you that there is a lot more work to be done. And that's why you see this as a common feature is every single new observatory that is being conceived, like the TMT, like the JWST, which flew 2 days ago, and the other big telescopes, they all talk about trying to figure out the connection between black holes and galaxies. And that is because in order to find out how these black holes have evolved along with these galaxies, you need to observe very far away galaxies, which means you're looking at the past. And in every way possible, in finding out the masses of their supermassive black holes, and finding out how they are accreting matter onto them and things like that. And so, so that is why high redshift observations, very, very important. The SKA has, one of its main goals is also to do this, study high redshift galaxies and look at the connection between what you see in the optical and what you see in the radio. And since this is a radio astronomy school, it is very, very important to point out that in the radio, you get absolutely independent information about the nature of the gas that's falling into the centers of galaxies and the activity in central galaxies. I didn't talk about AGN at all because that's another lecture. You've heard about the activities in the centers of galaxies that can be seen in the radio. And so studying the black holes as a function of redshift is the future of this subject. And to figure out how the black holes grow and how they are connected with the evolution of the galaxies. I'll stop there. Thank you. Let's see if anybody has any questions.
Sir, this mass of the black holes, are they equal to the mass of the star which have collapsed to form the black hole?
Right. So we're talking of stellar mass black holes here. And the star that causes the black hole, first of all, the entire star does not become the black hole. I think I showed you in the animation that I showed you, the outer parts of the star become a supernova and they're ejected. It is the inner core, the inner part of the star that implodes to form the compact object. It could be a white dwarf, it could be a neutron star, it could be a black hole. And yes, the entire mass of that goes into the black hole. But in the process of that core collapsing, a part of the star's mass is lost, right? Is that what you meant, or did you have any other question?
No, sir. Yeah, I meant that.
Okay. Anybody else?
So can a supermassive black hole exist without a galaxy?
Right. So that's a very, very good question. Now, see the very good question. You see, in the case of LIGO, we are seeing black holes merge, right? And so those are stellar mass black holes. We still can't see supermassive black holes in the same context because supermassive black holes will also, when they merge, will form, will send out gravitational radiation, but there'll be a different frequency which we are not sensitive to. Now, we have seen supermassive black holes merging, and I didn't show you pictures of them. There are 3 or 4 cases we know in which we know that there are supermassive black holes, 2 supermassive black holes in the same galaxy. And all of them we know have had recent mergers, right? So which means that these are the supermassive black holes of the 2 galaxies that are merging together. So when we found the supermassive black holes first, but then realized that there are 2 galaxies there. The supermassive black hole is very much connected with the galaxy. And it's hard for a galaxy to eject its supermassive black hole. Normal stellar mass black holes get ejected from the entire environment all the time. And because of collisions, there's enough energy that a black hole will be ejected. Now, in the scenario that I talked about, it looks like the galaxies and the black holes co-evolve, which means the black hole becomes a supermassive black hole using the resources of the galaxy as gas and stars fall in, and it grows. So it's very much at the bottom of the potential well of the galaxy, right? Now, for a galaxy to eject this supermassive black hole, the only way it can do it is if it actually goes and has a collision with another galaxy. And then the two, one of them will have some kind of a motion going into the other galaxy. But still, it's kind of bound to the galaxy, right? The rest of the galaxy will take part in the collision. So it is hard to imagine a supermassive black hole without a galaxy, except there is quite a lot of theoretical papers being written about when these supermassive black holes actually form. Just because they cannot form from the merger of stars, it is likely that they form in a very early universe, not very, very early, like in the first few seconds, but before galaxies form. It is likely that primordial black holes are seeded in the very early universe, but they might form before the galaxies. So one of the reasons we want to study the first stars, as we are seeing in JWST or SKA, is we want to know whether the supermassive black holes form first and then galaxies form around them. So are they the seeds of galaxies? There are theories that tell you that. We haven't found any of these yet, but if we can look at very high redshift, which means very early on in the age of the universe, we might find supermassive black holes without the galaxy having formed around them. And that would support this theory that the black holes seed the galaxies. But in the current universe, in the nearby universe, it is hard to find evidence of a supermassive black hole that does not have a galaxy around it.
Okay, sir.
Sir, can we have more than one black holes in a galaxy?
A typical galaxy has about 10 to the power 5 black holes.
No, like the supermassive black holes.
Yeah, I just told you that we found 3 galaxies, and I know there may be more in which we found more than one supermassive black hole. But all of them have evidence of recent merger, which means 2 galaxies have merged together. And so you are looking at 2 black holes that have come from the 2 galaxies. But in all other cases, we've seen only one supermassive black hole in the middle of a galaxy. It's hard to form that one. So it's hard to form more than one because it is in the bottom of the potential well of the dark matter potential of the galaxy. So there's a unique supermassive black hole. And what I'm trying to say is that if you find evidence of more than one, it is likely that they will merge to form one. And that is what you see in merging galaxies. As they merge, the 2 supermassive black holes come very close to each other and they merge within a very short time. So yeah, so we haven't found any evidence of more than one.
Okay, sir.
There are more questions, Kaustubh? Do we have time for more questions?
I think Somak, we do. We can continue for another 5-6 minutes and then we round up.
The masses of some of the supermassive black holes are about the same as the masses of globular clusters, right? So can we have some very dense globular clusters, and in them a lot of stars have collapsed into a black hole, and can there be some sort of a chain reaction such that the entire globular cluster gets converted to a supermassive black hole?
That's very hard to do. Because, I mean, how forming compact stars is difficult enough. And that is because um, stars are supported by nuclear reaction, nuclear fusion, and that causes thermal energy. And so the material has quite a lot of random motion, kinetic energy, and that keeps the star from collapsing, the gravitation itself. So stars are supported by hydrostatic equilibrium, as you know, and that comes from the energy that is being generated in the star. And when that goes away, the star collapses because there's nothing to stop the collapse. In a globular cluster, there is nothing to collapse a globular cluster. What would collapse the globular cluster? Because it has its own thermal motion, because globular clusters are not bound by dark matter, not much dark matter in globular clusters. They are bunches of stars that have velocity dispersion, and it's not that that's going to finish. Like in the star, the nuclear reaction in the middle uses up all the gas, and it goes, and so there is no thermal motion anymore, and so the star collapses. In a globular cluster, the kinetic energy is not going to go anywhere. So you cannot collapse a globular cluster. We have found compact globular clusters, but they're still, the most compact globular cluster I know is about 5 parsecs across. And if you want to bring them closer and closer together, if you look at the virial theorem, it will tell you that the kinetic energy is going to prevent them from coming any closer together. Whether you can have clusters of black holes, which are formed somewhere else and they come together, is very interesting. I don't think you can get 1 million black holes together, or 10 to the 4 black holes together, without them merging. So such things, very difficult to conceive. So that's why I said it's very safe to say that if you have something that has 10 to the power 6 times the mass of the sun, and it's less than a parsec across, then it is a compact object, a single object. It's not a cluster. Now, basic theoretical calculations have been done about what sizes masses can support, which are under gravitational equilibrium. Amrita, next.
Yes, sir. So my question is, why did we first try to obtain the shadow of M87 and not our own black hole?
Good point. I mean, actually, we didn't. I mean, the Event Horizon telescope targeted both, and our galaxy. In fact, the plan was to publish the image of our galaxy's black hole first. But I told you the resolution of two are the same, because M87 is 10 to the power 9 times the mass of the sun. Our galaxy's black hole is 10 to the power 6 times the mass of the sun. And this is 8 kiloparsecs away, and that is 15 megaparsecs away. So the resolution, the size is the same of the event horizon. And it turned out that the image they have of the of M87, which is close to the galactic pole, and so you're not looking through a galactic disk, you're looking away. The Virgo cluster is very close to the North Galactic pole. And so their image was much better signal to noise. And it was cleaner, and that's why they published that. They're still working, even though they started working on the Milky Way black hole image much earlier. They're still working on it because as I told you have to see through the Milky Way's disk. And so there's quite a lot of sources of noise in the disk. There are other things that also produce millimeter waves, radio waves. And that is why they have had a problem getting a very clean image. They have not published the image yet, and they're saying that they will publish it soon. So the M87, the reason is that's a cleaner image. That's you're not looking through the galactic disk, you're looking away from the galactic disk, and so there's a lot less confusion.
Vit Agarwal, I think you have your hand up. No?
Yeah, a question. Sir, how many galaxies are confirmed to have supermassive black holes till now, roughly speaking?
I don't know. Well, first of all, I showed you the kind of mass threshold. And above that, all galaxies that have been observed or looked at for evidence of supermassive black holes, they have. Now, if you want a number from me in which black holes, supermassive black holes have been found and some kind of mass measured, I think the number would be in the thousands, close to a few thousand galaxies for which actually such things are measured. But if you want a statistical number as to looking for evidence of such things in the middle of galaxies, I would say tens of thousands galaxies have been found. More importantly, no giant galaxy has been found in which there is no supermassive black hole when somebody's looked for them.
Thank you.
Somak, yesterday the question came up as well about existence of supermassive black holes in dwarf galaxies.
Yeah.
And actually a couple of years ago, I mean, it's not the nice mass measurements which you mentioned,
yeah.
But in dwarf galaxies with the very large array, a couple of years ago, Amy Rines, Jim Condon and others, they reported that they're very compact sources which could only be due to supermassive black holes, but not as massive as millions, but probably hundreds of thousands solar masses kind of. And interestingly, they were not at the center of the galaxies, but they were offset from the center, which some theoretical sort of scenarios also say.
I think I did mention, I mean, for dwarf galaxies, I know of, I think, 3 cases in which supermassive or massive black holes have been found. The one you mentioned, there was another one. So this is telling us something, this is the interesting bit. I mean, we are getting clues from the relation between the supermassive black hole and the galaxy. We know that they correlate, they're in the middle of the giant galaxies. They correlate with the older population. Some of the dwarf galaxies are a mixed bag, right? There are dwarf galaxies that are very old. There are dwarf galaxies that are very new. There are fragments. Also, there's a lot of merger going on in dwarf galaxies. We know that. Dwarf galaxies merge with themselves and with the major galaxies around them. So having, and in many dwarf galaxies, the center is not well defined because they are kind of scrambled and irregular galaxies. So one can probably think of, in a merging system, the black hole might not be in the middle. If, for example, it's come from one of the galaxies that is merged with the other. But, I don't know about this particular galaxy you're talking about, what the final verdict of it was.
I also haven't followed it up. This was a couple of years ago by Amy Rines, and they actually reported about a dozen sources. And also the other aspect is, some of them, or at least a few of them, seem to harbor AGN. And if they're believed to be due to accretion onto supermassive black holes, although we don't have mass estimates, they're probably smaller size black holes in them.
That's very interesting. That's kind of another evidence of this intermediate. There are so few detections of these intermediate mass black holes between the stellar mass ones and the supermassive ones.
Palak has a question, maybe the last question, then we'll take a gallery shot. Yeah.
Sir, in the case of our own galaxy, like as you said, like we are looking through the disk, like sir, we don't have any other way, like the emission is being reflected from other celestial objects and then coming to us, so we can detect that.
No, that doesn't work that way. Once you reflect, I mean, how can you do that? First of all, black hole is not emitting anything anyway, right? So you are, when you're looking at emission around a black hole, you're looking at the emission around the black hole from the gas that's around. And then you don't have large mirrors in the sky that you can reflect. Gravitational lensing is a way where you can actually probably see things where the light bends and comes around us, but the gravitational lensing effect from the center of a galaxy to us is not high enough. But you can see around, not in straight lines, but around if you have lensed objects. And there are, I showed you examples of, how gravitational lensing around a black hole works. But we are stuck in our galaxy, right, in 8 kiloparsecs away in the disk, and we can't go very nearby and look at it. So that's a problem with our own galaxy. And you can look at it high resolution because it's nearby, but also we are inside the galaxy, and so we are stuck. So if you want to know more about such systems, you have to look in external galaxies.
Okay, sir.
Okay, thanks very much, Somak, for a wonderful and very lucid talk on supermassive black holes.